Welcome to ES 310 Lesson 2. Today we'll be looking at objects that travel along a straight line. They may move back and forth along that straight line, but we only need to worry about motion in one direction for today. We will start by looking at a variety of definitions that lead to general mathematical equations that relate acceleration, velocity, and position, and time. Then we're going to look at the special situation where acceleration is a constant and look at how that simplifies those equations. The final section will look at graphical methods for solving these problems that should remind you of the shear moment diagrams that we did last semester in statics. For further details on the content of this lesson, please refer to Chapter 12, Sections 1 and through 3 in Hibbler's Dynamics book. We will also be using integration and derivatives throughout this lesson, so you might want to review those before you start. Let us start from the definitions we learned about in the last lecture. You'll remember that kinematics is a study of accelerated motion, as opposed to statics that has zero acceleration. Its focus is on the geometry of the motion, rather than on the forces that cause it, which is what we study in kinetics. The variables we are interested in kinematics are time, position, velocity, and acceleration. The type of motion we're focused on today is rectilinear motion. This is defined by straight line coordinates, x, y, and z. This is the typical type of motion that we're used to dealing with, but later in this semester we will be dealing with motion that's described in terms of other coordinate systems. Rectilinear motion can be continuous or erratic. Continuous motion has no sudden changes in speed, acceleration, or direction, whereas erratic motion changes suddenly. Erratic motion is often described by graphs. The first definition we need to look at is the differences between position, displacement, and distance. In common English, all three of these terms mean roughly the same thing, but in dynamics they are very different. So first of all, position. Position is a vector that locates a particle relative to some origin O. Normally we can pick where the origin O is. So for example, let's take a room. So if this is our classroom, let's arbitrarily decide that the origin for this classroom is going to be down here in this corner. And we'll give it some distances. So we'll say that this is 40 feet and this is 30 feet. So, 30. Feet. Alright. So now if I were standing in this corner of the classroom, my position is the vector that locates where I'm standing relative to the origin. So this is the vector. This is my position. Assuming, of course, that that vector were straight. So let me try that again. Alright, there we go. That's my vector. So that is my position, which is called S. Notice S here is bold, because bold indicates a vector that has both a magnitude and a direction. So I might say that I am standing 40 feet from the origin to the right. Right? So I have a direction, I have a magnitude, that's my position. Now, I'll call that S1 or S0. Let's get rid of that. Alright, sorry, S0. Alright. Now, if I were to move from that corner to this corner up here, I would now have a new position, right? S1. It's got a vector. It's a vector, so it's got 30 feet is its magnitude. Its direction is, I don't know, to the north or above the origin. Alright. Now my displacement is the change in position. So when I went from this x to that x, I have a displacement. I changed my position, and it's the difference between this vector S0 and this vector S1, right? So if you remember back to adding and subtracting vectors, the change in position would be this vector right here. which we call delta S, where delta means just change. And again, these are all bolded because they're vectors. So that's displacement, delta S. Now distance is something completely different. Distance is not a vector. Distance is a scalar. So distance is the total length of the path. So if I started at this corner and I started walking through the room and I had to go around some desks, and so I have a squiggly line and I ended up in that corner, the green is my distance, S total. Right? S total is a whole lot bigger than delta S. It also has no direction. It would be meaningless to talk about a direction of this green because it waves all over the place. So position is a vector relative to the origin. Displacement is a vector, which is a change in position, so it's relative to some other point. And distance is a scalar that is the total distance walked. All right. The next definition we look at is speed and velocity. So just like distance and displacement, speed is a scalar, velocity is a vector. The vector velocity is the instantaneous change in position per time. Okay, it has a magnitude, how fast is this going, and it has a direction. It's going north, it's going east, whatever it is. All right? Speed is just the scalar. It's the magnitude of that velocity. So if I were driving to Cedar Falls at 60 miles per hour, right, my velocity would be 60 miles per hour south. My speed would just be 60 miles per hour. The average speed and the average velocity tie back to the difference between distance and displacement. The average speed is a scalar. It's the total distance traveled in some amount of time. The average velocity is a vector, so it's the displacement per time. So if we look at the figure, remember our displacement is just the difference between the final position and the initial position, right? So that's delta S. Our total distance is S sub t, right? So that is a much longer distance. So in this case, our average speed, if in a given time, would be bigger than our average velocity. Acceleration, we are only interested in the vector part of it. It's the change in velocity per amount of time. And it needs a magnitude and a direction. So let's turn those definitions into mathematical expressions now, right? So we have an average velocity, we said was a change in position per change in time. If we make that instantaneous, we make those changes really, really small, what we end up with is a derivative. So the velocity is the derivative of the position. Now this dot notation, so S with a dot on it, just means a time derivative. It's a notation, it simplifies things, so you don't have to keep writing ds dt. All right? If we have that the velocity is the time derivative of the position, we can also write it as integrals. So the integral of ds is equal to the integral of v dt. So if we have expressions for these, we can find s by integrating this. The average speed, as we said, was the total distance. This is not a vector. This is a scalar divided by change in time. Then if we look at acceleration, we've got our average acceleration as a change in velocity per change in time. We make that instantaneous, so we make our changes very, very small. We get the derivative of the velocity with respect to time. So a is equal to v dot, time derivative. But v is s dot, so a is equal to s double dot, or the second derivative of s with respect to time. We can integrate v then, the inverse of these derivatives. We would have the integral of dv is equal to the integral of a dt. So those are the core two equations. We can often find another useful equation by combining the two. So if we don't know anything about time, for example, we wouldn't be able to handle these time derivatives. So if we solve each of these for dt, we get dt is ds over v and dt is dv over a. Combine those, so set them equal and redistribute. We get this expression that a ds is equal to v dv. which is often a useful expression when we don't know things about time. Again, we can integrate that, and we have a similar relationship. So let's take a look at an example of using this. This is one where it is time dependent, so we're going to use one of these first two equations here. And they give us the speed of a freight train. So we have an equation that's the speed of the freight train, and where t is elapsed time in seconds, so t is measured in seconds. We need to figure out how far does it go in 3 seconds, and what is its acceleration in this time. So the distance, s, at 3 seconds, and the acceleration at 3 seconds. And we're going to assume that at t equal to 0, s is equal to 0, right? They just want to know the distance traveled, so it could be, if it started at 5, it's going to be some distance past 5. But it's easier to handle if we start at 0. All right. So if we remember back, we're given v and we're looking for s. And v is a function of time. So here's our expression. Here's v, here's s, but this is s dot. So we probably want to use the integral version of this. All right, so we've got the integral from s naught, our initial s, to s of ds is equal to the integral from 0 to our time that we're interested in, v dt. All right, so we plug in for v, so it's the integral of dt, 0 to t of 60 times 1 minus e to the negative t dt. All right, so 60 is a constant. So on this side, we just integrate. So this is going to be s evaluated from s naught to s, which is going to be, let's see, s, which is what we're looking for, minus 0, which is what we said here, so s naught is equal to 0, right? It's equal to, all right, 60 is a constant. The integral of 1 dt is just t, and the integral of negative e to the negative t is positive e to the negative t, right? So the negative 1 comes down, e to the negative t stays the same. That's our integral of e to the negative t. And we're going to evaluate that from 0 to t is equal to 3, which is the time we're interested in, right? 3 seconds. All right, so if we plug this in, then we get that s is equal to 60 times 3 plus e to the negative 3 minus, minus 60 times 3, 60 times 0 plus e to the 0. And plug that into your calculator, you get 123 feet. So in 3 seconds, this freight train moves 123 feet. Now, the next part of this is to find the acceleration. So if we look back at the previous slide, the acceleration is the time derivative of the velocity. So a is equal to dv dt. So what is the time derivative of 60 times 1 minus e to the negative t? All right. Well, 60 gets factored out, and the time derivative of 1 is 0, and the time derivative of negative e to the negative t is e to the negative t. All right, so the negative sign comes down. All right, so this is equal to 60 e to the negative t. At time equal to 3, then a is equal to 60 e to the negative 3, which gives us 2.99 feet per second squared as our answer. As another example, let's look at a situation where we don't have anything knowledge of time, right? So this is a position-dependent equation, right? Velocity is written in terms of position. So we have a particle, it's moving along a straight line, so we can use these methods because it's a straight line. Its velocity is defined in terms of position. So velocity is equal to -4s squared, and s is in meters. So if at time equal to 0, s is equal to 2, what they give us, these are the initial conditions. And we need to find what is v as a function of t. So we're looking for an expression, and what is a as a function of t. Let's start from this definition, right? ds dt is equal to v, which is equal to -4s squared. All right? So now if we integrate both sides here, well, let's look at this. We have s on both sides, so let's move it around so all the s's are on one side. So we have 1 over s squared ds, and we'll put the dt on the other side. So -4 is still there, dt. Now we can integrate both sides, right? So we're going to integrate this side from our initial position, which is 2, to whatever our final position ends up being. And we're going to integrate this side from our initial time, which is 0, to whatever our time ends up being. Alright, so then we can solve this. This is the same as writing the integral of s to the -2, right? ds, which is -1s to the -1, which is -1 over s evaluated from 2 to s. And that's going to equal the other side, which is just -4. Integral of dt is t, evaluated from 0 to t. So we have an expression for s in terms of t, which isn't what we're looking for yet, right? So we can write our expression for s in terms of t. We get, what, -1 over s, that's this expression, minus -1 over 2 is equal to -4t minus 0. So we get then, doing some math, we get that s is equal to 2 over 8t plus 1. Right, just rearranging this and solving for s. Alright, so that's a starting point. Now we have s in terms of t. So now we can go back to our other equations, right? So if we have s in terms of t, v is equal to s dot, right? The time derivative of s with respect to t. So we're going to find the time derivative of this expression. So remember how to find time derivatives of fractions? We do v then is equal to the derivative of the top, which is 0, times the bottom, plus the top itself, 2, times the derivative of the bottom, which is 8, divided by, sorry, this should be a minus sign. Product rule has pluses, the quotient rule has minus signs. Alright, divided by the bottom squared, 8t plus 1 squared. That then is our expression for v. We can simplify that. It will be 16 over 8t plus 1 squared. So that is one of our answers. To find acceleration, we do it again. Acceleration is equal to v dot, which is the time derivative of v. So acceleration is equal to the time derivative of this expression, so derivative of the top times the bottom minus the top, which is 16, times the derivative of the bottom. We have to use chain rule, so outer derivative, 8t plus 1, times the inner derivative is 8. Alright, and then divided by the bottom squared. So 8t plus 1 squared. There's 8t there, and that 8t will cancel. And we can simplify this then into 256 divided by 8t plus 1 negative. And that then is the other part of this answer. Now let's take a look at the specific case where the acceleration in our system is constant. So this is somewhat realistic, common in the real world, right? So not necessarily with cars and trains and things of that sort, but the acceleration of gravity is a constant. So anything that is falling will use these types of equations, which is a simpler version of the derivatives and the integrals that we saw before. So if you have a constant acceleration, you will not need to integrate or take derivatives. All right, so something to just remember. If you have a constant acceleration, no integrals. So you want to see problems that have constant accelerations because they're easier. So let's take a brief look at some of these derivations. Remember that acceleration is equal to the time derivative of velocity. All right, so in integral form, we've got the integral of dv is equal to the integral of ac dt. Now, if ac is a constant, it pulls out. Integral of dt becomes t, and the integral of dv is v minus v naught, right? From v naught to v. We can rearrange this just into the standard form that we're used to seeing. V is equal to v naught plus act. All right. Now let's take a look at our v, right? So v is equal to the time derivative of position. So integral form, integral from the initial position to the final position of ds is equal to the initial time to the final time of v dt. So let's plug in v from up above. We'll put it down here. Right, so the integral of v naught, that's a constant. It's whatever the initial velocity was. Plus ac, a constant based on our simplification here, and times t. So we take that integral, we have the integral of ds from s naught to s is s minus s naught. It's equal to constant v naught times t plus constant times t, so 1/2 act squared. So that's our second equation in the simpler form. The third equation was our v dv equal a ds equation. So integral form of that, the integral of v dv is v squared, evaluated from v squared, is actually 1/2 v squared, right? Evaluated from v naught to v, right? So you've got the v squared minus v naught squared. The 1/2 went over here and became a 2. Constant ac, s minus s naught. All right, so these are the three equations that are very handy when you've got a constant acceleration. Remember, if your acceleration isn't constant, you need to use the integrals or the derivatives instead. But if your acceleration is constant, you can use one of these three equations. So let's take a quick look at an example here. So we've got a car traveling at an initial speed of 70 kilometers per hour. It accelerates at 6,000 kilometers per hour squared, which is constant, right? Constant acceleration. So we can use the simplified equations. It's moving on a straight road. How long will it take to reach the speed of 120 kilometers per hour? So we have an initial speed, so v naught is 70. We have a final speed, so v is 120. We want to know how long it will take, so we're looking for time. And we also want to know how far does it go during this time. So the distance it goes is our final position minus our initial position. We don't know our initial position, but we're looking for this change, this quantity. All right, and we're also given our constant acceleration of 6,000. So let's take a look at our equations. We're trying to find time. We're given initial velocity, final velocity, and acceleration. So if we look at our equations, we're looking for, let's see, we know v, we know v naught, we know ac, we're looking for time. So to find time, we want to use this first equation. So v is equal to v naught plus act. We'll do this down here. V is equal to v naught plus act. All right, so v is 120. V naught is 70 plus 6,000 t. So for t, we get 0.008333, and our units, our time units were hours. All right, so this is hours, and you could convert that to seconds if you wanted to. All right, the other thing we're looking for is this displacement. How far do we go? S minus S naught. So if we look at, well, now we could use either of these two equations, right? Because if we look in the middle equation, we've got S naught. This is what we're looking for, this quantity. And then we've got V naught. We know that. We know T because we just solved for it. We know AC and we know T. So we could use that equation, or we could use this one because we know V, we know V naught. We know AC, and this is the quantity we're looking for. So either one. Let's use the first one. So we get that S minus S naught is equal to V naught T plus 1/2 ACT squared. This T is going to go up there. And solve for these, we get S minus S naught is equal to 70 times 0.00833 plus 1/2 times 6,000 times 0.00833 squared, and we get an answer of 0.79, and our units would be kilometers. Our final topic for today's lesson is looking at graphical methods for solving these types of problems. So there's two possibilities here, right? You could either be given a time plot or a position plot. So let's look at the time plot first, right? So time plot, you'd be given an S versus T, or a V versus T, or an A versus T type plot. So if you're given an S versus T, you remember that S is related to V through the derivative, right? So the derivative of S is V. Well, graphically, a derivative is just a slope. So the V plot would be the plot of the instantaneous slope at each time on the S plot. Same thing from A to V, right? So the time derivative of V is equal to A. So the acceleration plot is the plot of the slopes of the velocity plot. If you want to go the other direction, we're looking at integrals. Well, integral is just an area under the plot. So if you're given an acceleration plot, you find the cumulative area under that plot. That will give you, and you plot that, that'll give you your V. You take the cumulative area under the V plot, you get an S. This will make more sense in an example. If you're given a position plot, things are slightly more complicated, right? Because now we don't have the straight time derivative type relationships. We're using that third relationship. So the acceleration from a velocity, in terms of position, is the slope times the magnitude. Right? Just looking at this equation, which came from the A ds is equal to V dv, right? That was one of our equations. So the slope is the dv ds, and the magnitude is the V. Going back up is even more difficult, right? Because now you've got this squared relationship, right? But this side of the equation is just the area. So the area then, so the velocity is going to be related to the area, but is going to be offset by the square of some constant, and it's going to be squared itself. So this would be more of a you'd have to do the math here. It's not as easy as these. We're going to focus on the time plots for this class. So let's take a look at this. Often we want to use this because we have erratic motion. So erratic motion is typically described by a series of equations, right? It can't be described as only one. So, for example, in this bicycle example, right, we've got this girl on a bicycle. Initially, her position is parabolic, right? It's an s equals to t squared type form. And then she reaches the point where she starts going at a constant velocity, so it's just a straight line, okay? So this is just an example, but this is the idea of erratic because there's a shift, right? There's a sudden change in her velocity. So let's think about this. If we're given her position graph right here, then we're going to plot the slopes of the position to get the velocity. So down here the slope is 0, and it gets bigger and bigger and bigger, and then it's constant. So slope starts at 0, gets bigger and bigger and bigger, and then it's constant. How do we know this value? Well, it's given to us as part of this equation, or we can do rise of a range, right? So 500 minus 100 is 400, divided by 30 minus 10 is 20, so 400 divided by 20 is our slope, or 20. Now to go from V to A, we do the same thing, right? So what's the slope in this section? Well, it's constant. It's a constant of 2. So we've got a constant slope, and then what's the slope for the second section? 0. We can also go backwards, right? So here, if we're given the acceleration, then we're going to be plotting the area. Well, the area at, 1 second is really small. The area at 2 seconds is slightly bigger. What is that area? Well, it's 2, magnitude of the rectangle, times the base, 2. So the area keeps getting bigger, right, until we get up to 10. So at 10, the area is 2 times 10, right? So 20, that's what the 20 is. And then after that, it doesn't change, so it just stays at 20. Then we're going to plot the area of this shape up there. So it starts really small, it gets bigger and bigger, and is getting bigger in terms of a triangle though, right? So the area at, say, 5, right, if we draw the triangle at 5, that would be 5 times what we're halfway up, which would be 10. So 5 times 10, so at 5 we'd be plotting this, right, would be 50. Is that right? And so forth. So you're plotting the area over here. At this, the value here, right, would be the area of this triangle. I forgot the half. So 1/2 of 10 times 20 would be the value there, 100, and so forth. And then you'd add the rectangle. All right, so let's actually do one of these. Here we go. We've got a 2-stage missile, and the plot shows the acceleration of the 2-stage missile, right? So in the first 15 seconds, first stage A burns out, and then the second stage B ignites at 15, and then it burns out. And we're supposed to plot the T versus VT and ST graphs based on this AT. So we are going, if we go back up 2 slides, we start at A, we're going up, so we're going to be dealing with areas. All right? So let's do VT first. I'll draw it right underneath here. VT. Something's gonna change at 15. So I've got a dotted line there, and we're done at 20. So there's the 20 line. That's 15, and this is 20. So what do we got? Initially, we have a straight line. If we take an integral of a straight line, we're going to get a slant, right? Or in terms of thinking of areas, we start with a really small area, right, down here at 0, and we're going to increase the area until we get somewhere there. And then we're going to change the slope of the line, because we're going to increase the areas faster, so it's going to go like this. Going back upwards, right, the slope here is plotted there. So the slope of this line is 18. The slope of this line is 25. So we drew it correctly. Now we need some values. How do we find this value? The value here is going to be the area of this rectangle, right? So that's going to be 18 times 15. The value here is going to be, an 18 times 15 is 270. So the value here is going to be this value plus this area, right? So this is 270 as an area. So this is 270 plus, what's the area of this rectangle? Well, it's 25 times the base, which is 5. So this is going to end up being 395. And that completely defines everything, right? Because these are straight lines going from 0 to 270, and then another straight line from 270 to 395. Now let's do the S versus T curve. So if the V is a slanted line, the S is going to be quadratic. Alright, so we are going to get one quadratic term here, and then we've got another quadratic term there, and it looks like, well, hold on, let me draw this a little bit better to scale. So we've got our 15 mark, right? And we've got our 20 mark. And they're both going to be quadratic, and one's going to be slightly slantier quadratic than the other. So this one's going to be quadratic, and this one's going to be even more quadratic. Something like that. Sketched very poorly. This doesn't look very quadratic, does it? Let me try again. Something like that. Alright, now how do I know it's quadratic this way and not this way? Right? That's a good question. Well, the slope of this needs to be plotted there. So the slope of S needs to be 0 at time equal to 0. And that's why it's flat here. Right? Then it gets up to some bigger number. It's continuous. The slope needs to be the same over here as there because this line's continuous. It changes in slope, right? But the value is the same, right? So the slope here needs to be 270. The slope on just the other side also needs to be 270. And then the slope up here is going to be 335. The slope is. What are the values? That's where we look at the area. Right? So what is the area of this triangle? Right? That's what's going to be put in here. So the area of that triangle is 1/2 of 270 times 15, which gives us 2025. All right, value up here is 2025 plus the area of this shape. Let's make my hash marks go this way. Alright, what's the area of this shape? Well, there's a rectangle part of that shape, which is going to be 5 times 270. And there's a triangle part of that shape that's going to be 5 times, it looks like 25 times 5. Right? It's the height of that triangle, which then gives us 2,427.5 as our answer up there. And once again, we've defined this. This is quadratic, and we've got our 2 endpoints. Let us close by looking at one more example of erratic motion. In this example, we're given the S versus T graph, and we're supposed to draw the V versus T and the A versus T graphs. The shape of this curve looks really similar to the example we saw a couple of slides back. But what I want to focus on here is how to put this into mastering engineering. So let's go switch over to mastering engineering. Here it is. We'll reset it since I was playing with it before. Alright, so here's our problem. If we look at the graph, we'll notice there's 2 regions to this graph, right? There's the first region where we have a quadratic function, and the second region where we have a linear function. So the first thing we want to do is set up 2 regions in the V versus T graph. To do that, we're going to add vertical lines. So if you click on vertical lines, it changes to on, and now we can add some vertical lines. The first one's going to be at 0, where the region starts. Second one's at 5, where we switch from quadratic to linear, and the last one is at 10, where we're done with our time segment we're interested in. Now, if I put my cursor over here, it changes to a hand. Then I can click, and then I can change this number down here to be exactly 10. This one should be exactly 5. And this one is already exactly 0, so we're good. Now I'm done adding vertical lines, so I can turn that off. And now we need to figure out what goes in each of those regions. So remember, to go from S to V, we're taking the derivative, or we're plotting the slope. So if we look at our graph, we've got some slope here, right? At 0, the slope is 0, right? It's flat. Then it increases steadily to whatever it is at this point, And then after that, it's going to be constant. All right, so a quadratic function, when you take the derivative or look at the slope, it becomes a linear function. So we're going to want to add a linear function to our v-graph. Under add segments, that's where we're going to add our functions. We have various options. We could add a constant, we could add a linear function that either goes up or down, we could add quadratic with various shapes, or we could add cubic with various shapes. So we want a linear function. The question is which one, right? So we said it started at 0 and then it went to some positive number. So we want something that starts low and goes positive. So we want this one. We put it over here, we can put it anywhere we want. So we'll put it somewhere here, and then I'll type in 0 because we know it's 0 at the initial point. Now the question is, what is the slope at t equal to 5? So there's 2 or 3 ways we can do this, right? So if we look at the quadratic function, we can take the derivative, plug in t equal to 5. That would be the slope at that point. So the derivative of 3t squared is 6t, plug in 5, we get 30. Another way to do that is to notice the slope just at the end of the quadratic is the same as the slope just at the beginning of the linear. So we could look at the linear function, and if you look at the equation, it's very easy to tell what the slope is, right? It's whatever's in front of the t. So we'd have a slope of 30. Another way of looking at it is, here's our linear function. We look at rise over range, right? So we have 75 to 225, that's 150 is the change. 5 to 10, that's 5. So 150 divided by 5 is 30 again. So we know that this number needs to be 30. All right, now, next section of the graph is linear in the S-graph. So if we take a derivative, it's going to be constant, or look at the slope, it's going to be constant in the v-graph. So we need to add a segment, a constant segment. We want to make it go straight across here. And we can add in and make this exactly 30 by typing it in the box. All right, we're done. That is our first graph, so let's submit it, and hopefully it tells me I'm correct. Yep, tells me I'm correct. Now we can go on to the next one. So in the next part, we need to graph the A versus T graph. It's much easier to graph the A versus T graph by looking at the V versus T graph first, right? So instead of looking at the S versus T again, we're going to look up here. First of all, the same 2 regions exist. So let's add those same 2 regions. We're going to add a vertical line. One at 0, one at 5, one at 10. We will modify those to be exactly 10, and exactly 5, and exactly 0. And now we need to add our segments. So in the V graph, the first segment is linear, so it's going to be constant in the A graph. So we're going to add a constant, and I don't know what the slope of that constant should be. So what is the slope from 0 to 5 for this graph? Well, we change by 30 in the V and 5 in the T, so 30 divided by 5 is our slope. So that would be 6. Alright, then we have a region where it's constant. Well, the slope of a constant is 0, so that is still a constant. It's a special constant, and it's a constant down here at 0. Alright, there we go. So let's see if we're correct. Correct, I think. Yes, correct. So we are done with this problem and with this lecture.